In this next section, we're going to address the issues of multiple regression, specifically how multiple regression helps us in staffing, and then we're also going to get into the beginnings of understanding reliability and some of the issues around reliability. So what multiple regression is a way of finding the line of best fit between multiple variables, basically more than one or two. I mean, typically you can do it with two, but it's usually three or more, particularly when we're trying to predict an outcome that matters to us. So we try to find where the maximum validity is, the maximum overlap between the variables to predict the proper weights of each variable and how much each variable contributes to the outcome that matters to us. And so we might say that conscientiousness and intelligence and high scores on a work sample test would be a good way of predicting job performance. And so our goal would be to see what each one of those individual variables are weighted in order to be able to predict job performance down the line. So it looks at how each predictor is correlated with the outcome and how the predictors themselves are correlated with each other. I mean, ideally you want them to be minimally correlated with each other and maximally correlated with the outcome to have the maximum impact. And so we have to control for the impact of other variables. So with other things being equal, what impact does each individual variable have on the outcome? So continuing on with our discussion on multiple regression, here is a great visual about how multiple variables are predicting a particular outcome. So your outcome that you're looking at is Y. That's always the thing that you're trying to predict. And you have two variables, X and Z. Now X and Y are correlated and Z and Y are correlated, but X and Z are not correlated. And so this is ideally what we're looking for. We want to choose predictors that uniquely predict job performance, the outcome that we're looking for. And so the goal is to have minimal overlap between them and maximum overlap with each one to their predictor. So the more variables we have, again, we want the minimal overlap and maximum impact on the outcomes that we're looking for. So, so you can see where their unique contributions are. On this slide, this is what we don't want to see. We don't want to see X and Z highly correlated with each other and also highly correlated with Y, because you don't need both predictors. You need X or you need Z. You don't need both, because they both cover basically the same category of work and the same territory, if you will. So what you want is predictors that are covering unique aspects of your outcomes that you want to look for. And in this scenario, we're seeing X and Z correlated with each other, so there's no point in using both because it gets expensive, right? You want to use one or the other, but not both, and they should then predict Y. Ideally, you still would want more than just one predictor or two predictors, but in this situation, you really only need one predictor because one predictor seems to do a pretty good job of predicting the outcome that we want. So in this third example, this is actually what you're most likely to see when it comes to using predictor variables and outcomes. So the very first slide we saw there was no relationship between X and Z. In the second slide we saw a very high correlation between X and Z. Most of the time what you're going to see is a small overlap between X and Z. I mean, that's, if you're doing a pretty good job, this is more likely the realistic idea. And what that means is that sometimes variable X will predict Y, and it predicts it in the same way that Z predicts Y in some instances. So our goal is to have as much unique category predicted by X and unique category predicted by Z, so that it's covering unique parts of Y. So it's covering unique aspects of Y. So if a job has multiple factors to it, X predicts one factor, Z predicts another factor. There might be a little overlap between X and Z, but ideally X should uniquely predict Y, parts of Y, and Z should predict parts of Y with minimal overlap between the two. There is going to be overlap, but we want it to be minimal. So here's what multiple regression looks like in reality. So we're trying to predict job success in this situation. And so like with any line, you've got a constant, which is the y-intercept, and then you've got each test score and a particular weight to those test scores. And the weights are B1, B2, B3, and the test score is the standardized test score that we're plugging into the regression. So for example, our line of best fit through doing our historical regression of historical data. Predicting job success has a constant of 10, and then the interview is weighted 2, the personality test is weighted 1, and the job knowledge test is weighted 0.2. Those all uniquely contribute to job success with that particular weighting. So how do you basically translate this into practical use for you in the workplace? So if someone scores a 50 on the interview, you would plug that 50 in for the interview score, and you would have within those parentheses 50 times 2, right? So that we know that would be 100. If they scored 27 on the personality test, again, we would take that 27, plug it into the personality score, and we have 27 times 1, which is 27. And then we would have the 20 on the job knowledge test. Again, plug that into the formula, and you'd have 20 times 0.2 within the parentheses. And in the end, if you did the math out there, you would end up with 141. So 141 is then compared with predicted job success scores of other candidates and decide who would be the best one to hire. So you might have a series of candidates with all different interview scores and personality test scores and job knowledge scores. You'd plug them into the formula, and then you would rank them from highest to lowest to see who has the highest score to who has the lowest score. Now, again, I would always recommend putting in standardized variables in there as opposed to variables that are not standardized, because again, it's hard to compare an interview to a personality test. They're on different scales. But regardless, you can still do the correlation. You can still do a regression in that manner. So you might have another candidate who had 40 on the interview, 30 on the personality test, and 10 on the job knowledge test. And then you would plug all those numbers in, and you would see how they would score on it and whether or not they would beat the 141. And so once you have your list of people, you rank them. And as I said, you try to pick the ones with the top scores to make offers to. Moving on from the discussion on multiple regression, we're now going to talk about reliability. And in essence, how do we predict the reliability of a particular measure or an instrument that we're going to be using? And so we know that reliability is about consistency in the way that the measure gives us results. So we want to know that every single time someone scores high on a particular test, it reliably means that they will reliably have a high score in job performance. There is a lot of error that can influence reliability, things that are out of our control. And the more things are out of our control, then the more likely we are to have a measure that is not reliable. But when we can have a measure that is very consistent, it means it's controllable in its environment. So it's going to have very little influence from external factors. But you can have error that is random, that you can't control for no matter what you do. And then you can have error that's very systematic. And a great example of this is, let's say that you have a tape measure and it was produced by a manufacturer that had an error in one of the notches that indicates an inch or a half inch or a quarter inch. And let's say one of the inches is actually a little bit smaller, and it was an error, a systematic error in the tape measure, so that your inch is actually slightly smaller than an inch. And that's a systematic error because it's something that it's going to affect it across the board all the time. So even if you don't have the best reliability, it will be at least consistent within a certain frame of reference. So measurement reliability requires us to know and to be clear about what kind of measure that we're going after. We want to make sure that we are reporting the proper reliability for the measure, whether it's test-retest reliability or it's internal consistency reliability, or whether it is parallel forms reliability. We need to know that. And then we need to know how the measure is going to be used. If it's going to be used similarly to the way the measure was intended to be used and the way it was tested for its reliability. And once we have consistency in assessing the reliability and we know it's going to be used consistently, then we can make a good judgment about whether or not this is going to be a reliable measure for us to use in our own work. Remember that I said reliability is dependent on sort of its context and how much influence or impact the context has on the measure, how much bias can influence the measure. So what are some of the reasons why you might see differing scores between tests or among different people who are taking tests? There could be temporary physical or psychological states. For example, I might be anxious today, and that's going to influence the consistency of the results. So I might have been calm yesterday, but I'm anxious today, so we see some inconsistency in the results. There are also environmental factors that could influence things. The room is hot, the room is cold, the window is open, it's noisy, it's quiet. These all can influence reliability. The different form or version of the measure. There may be some forms of the measure, if it's done online, it's very different than being done face-to-face. Depends on the instrument. So we need to compare those forms to make sure that they are giving us consistent results. And then different evaluators. And we see this with interviews primarily. Even if we have a structured interview, if interviewer 1 looks at a candidate and then interviewer 2 looks at the candidate and they come up with very varied scores, that means that there's some error in the way that the interviewers are looking at the candidate. And so we might see inconsistency across the different evaluators who are looking at the candidate and making a decision from there. There are different kinds of error that can influence a measure and influence its reliability. You can have random error, which again, there's no consistent cause. It just happens. It's a hiccup. It's not a big deal. And that consistently, if it's random error, randomness occurs pretty consistently, and so we can discount it that way. Systematic error, when there's something that's very predictable, very purposeful, sort of having an impact on thing. And as I said, systematic error is a systematic, purposeful mistake, for example, in your tape measure, where your inch measure is actually slightly less than a standard inch. And so we know that's systematic. And everything that is measured will systematically have that error in it. You can also have deficiency and contamination errors. A deficiency error means that there are some aspects that you are not measuring, so your measure is deficient of what should be in a particular measure. So you might be missing something. Particularly if you have a measure that only measures one aspect of a job when a job is actually multidimensional. And so if you have a measure that only measures one aspect of a job, you're going to end up with a deficiency problem. You can also have contamination, where you have an error where factors that are really unrelated to the measure are being measured in your thing. And I know that I've talked about this in other classes where you have a performance measure, and your performance measure is to look at how attractive a waitress is, whether or not they'll be a good performer. And we know attractiveness is not relevant to being a good waiter or waitress. Being able to count money, give good service, take orders accurately, make sure that the table is taken care of in terms of drinks. These are all factors that are important to a waiter or waitress. But the fact that they are attractive or not attractive is not really relevant to their ability to give good service to somebody at a table. So a measure that includes something that's not relevant or may even be illegal is contaminated, and we want to be careful of those kinds of errors as well. This slide is a really great example of the difference between deficiency and contamination and what is relevant. When we have a construct and we have a measure, so the construct is the thing that we're trying to get at. So I'm going to develop a measure of intelligence, and I'm hoping that my measure of intelligence is fully reflective of what is considered to be intelligence. And so I have this measure, and it's supposed to overlap with the construct, the thing that I'm trying to measure. So your construct has a range of elements or aspects to it that we want to try to capture in our instrument. If there are things that are missing from the measure but that are in the construct, that's where you see that the dots and where it says deficiency. And those are the things that we should be measuring and we're not. On the bottom, where we see the measure, and it's sort of like a half moon or a crescent moon at the bottom, and the lines go from the lower left to the upper right, those are contaminations, which are things that are not relevant to the construct, but we appear to still be measuring. And those are the things we also don't want to include in our measure. We want to minimize those. The stuff that is where the overlap in with the two circles is the relevance, where it is in the construct and it is in the measure, and those overlap well. So we know that the things that are in the construct are in the measure itself. And that's the relevance, and that's where the lines go from the upper left to the bottom right. And the goal is we want that relevance area to be as large, if not as large as the construct area as possible. We may have a measure that doesn't capture everything that we want, but the last thing we want, we definitely want to guard against contamination. We don't want contamination. That's a bigger problem for us. Deficiency can have its issues, but at least the things that are in the measure are relevant. But what we don't want are things that are contaminating the measure in that context. So it's one thing to gather reliability information or data, right? I mean, there's different ways to measure reliability, retest reliability. We look at correlations between the first time you take it and the second time you take it, or we look at correlations between two reviewers who are reviewing it, or correlations between two different instruments that are getting at the same construct. But how do we interpret it? How do we know what is a good reliability measure and what is not a good reliable measure? So table 8.2 in your textbook does a really nice job of showing you the different correlations that you can see, and that we call those correlations reliability coefficients, because they're getting at, it's the correlation that indicates a particular reliability of the measure. Anything that's 0.9 or above is absolutely superior. And if you can see a correlation between two instruments, or 2 times that someone takes an exam, test, retest, or parallel forms exam, whatever it is, different evaluators, all of those, if you see a correlation of 0.9, a reliability coefficient of 0.9, that's superior. 80 to 89, 0.8 to 0.89 is really good. You're still fine there. Even something that's in the 70s, 0.7 to 0.79, is adequate, particularly if you're developing a new measure or it's the first time you're looking at the relationship between two variables. 0.7 to 0.79 in terms of reliability is still pretty good. Anything below that is very limited, because it means that there's a lot of error or a lot of variability that's going in those measures. So certainly anything below a 0.5 is useless to us, in terms of predicting performance. But ideally, we want something that is at a 0.7 level or higher for reliability. Which means that we're fairly confident that people are consistent in the way that the information is interpreted. That's the goal in that. So we've talked about different forms of reliability, but just to refresh you, there are 4 different types of reliability. There's test, retest reliability, which means the first time you take it and then the second time you take it, there should be consistency over time. Alternate or parallel forms reliability shows how 2 different measures, how a person performs on 2 separate measures of the same That's trying to get at the same construct. So you might have something that measures intelligence, but there's two different tests measuring intelligence. You want to look at the relationship between the two to make sure that they are consistent. Internal consistency reliability is looking at the extent to which all of the items that are going to be combined in some way to create a measure are getting at the same construct. And then lastly, what we're trying to get is inter-rater reliability, and that shows how the relationship between one reviewer looks at a candidate, for example, evaluates a interviewer, and how an interviewer evaluates an interviewee, and then how another one evaluates the same interviewee. And so we want to see the two raters should be evaluating things fairly consistently in terms of evaluating the person who did the interview. The last thing with respect to reliability is understanding standard error of measurement. Each measure has a specific standard error of measurement. It basically means that if someone took a test repeatedly, time and time again, it would be the range or the spread of scores you would expect to see if that person had taken it multiple times over. So it's in essence your margin of error that you can expect reliably because of the imperfection in the measure in and of itself. The confidence interval represents the degree of confidence that their true score lies within that standard error of measurement, and it's sort of plus or minus that standard error. So the goal is that we'd like to keep it within a very close range, and we hope we have the higher confidence we have, the closer it is to what we will believe that there's going to be an overlap between the true score and the measured score. So the lower the standard error, the more accurate the measurement. So when you see a standard error, or SEM, as it approaches zero, you know that this is as close as possible to what the true score is. The observed score is their true score, that there's no room for error in that. And there's very little that we have that has no standard error of measurement. There's always some degree of error in anything that we measure because it can be influenced by all sorts of external factors. But we want to keep that standard error of measurement as low as possible when we are trying to assess something. And so how does all this talk about reliability matter to you as an HR professional? Are you going to be calculating these reliability coefficients? And the answer to that question is probably not. You need to know how to do it, I think, but I don't believe on the job you're actually going to be asked to do this often. Maybe test-retest reliability, maybe inter-rater reliability, but some of the other things, probably not. But if someone is trying to come up to you and sell you an instrument, you need to know the right questions to answer. How is the standard error of measurement for your measure? Is it a high reliability measure? How much variance is there in your reliability? Tell me about your test-retest. Tell me about your internal consistency reliability. All those things. You need to know this terminology so that you can apply it when you are working with vendors who are trying to sell you instruments to use on the job. So you want your measures to be as highly reliable as possible with a very low standard error of measurement.